So molecular orbital theory, Max's idea is two atoms share one orbital. Anything you'd add to that, anything you'd modify? Does it have to be two atoms? We know that two atoms is the bare minimum for a molecule. So for molecular orbital, it would make sense that at least two atoms need to share this orbital. Why does it have to stop at two? You guys ever heard of the YouTube channel called Veritasium? Yeah? I would highly recommend watching their new video on basically slow motion cameras. They just posted it last night. I'm a glutton for their stuff. There are some scientists that have supposedly filmed, for lack of a better term, filmed the movement of electrons through molecular orbitals. They have essentially filmed what molecular orbitals look like. Do you guys know how fast electrons move? Not like a speed, but like a vibe. Real fast. The speed at which an electron moves is on the order of what they call attoseconds, which is roughly 10 to the negative 18 seconds. And this attosecond is to the second what a second is to the age of the universe. Okay? So how many attoseconds in 1 second? 10 to the 18 attoseconds every second. And the number of seconds in the age of our universe, I did some back of the envelope calculations earlier today. There are about 4 times 10 to the 17 seconds in the 13 billion year lifespan of the Earth. Sorry, of the universe, not the Earth. The Earth is much younger than that. The universe has been around for about 13 billion years, we suspect. That is 4 times 10 to the 17th seconds. And there are more attoseconds in every second. So I want you to think about the movement of an electron. An electron's movement is on the scale of an attosecond. So by the time an electron has lived through an entire second worth of time, from its perspective, it has just gone through the life of the universe compared to your perspective. Could you imagine living at the whole life of the universe, how long that would take? That's how long it feels for an electron to just move through 1 second of time. That's an incomprehensible amount of time. That's an incomprehensible speed, yeah? So orbitals are super weird because they like describe where electrons are. They describe how electrons move, and the electrons that are in them, we basically just say those electrons are everywhere. So this is our basis for molecular orbital theory. Okay, I think I'm going to switch to some brighter colors because I don't think these are showing up on the camera very well. All right, so molecular orbital theory. At least 2 atoms share an orbital, and that's where the electrons are found. Anything else that you guys wanted to discuss? Why is it that some of the other professors here kind of think of it as an aside you don't really need to know? Why is it that I spend the time on it? Why do I burden you with knowing molecular orbital theory?
So that when we figure something really cool out, we can credit you.
No, I don't want any credit. Thank you, though. You have many more people to credit than just me.
For reactions?
Reactions can be predicted a little bit more easily using MO theory. What else?
The way to explain how bonds break.
How bonds form and how bonds break. MO theory does it a lot better than valence bond theory. Do you guys remember our the benefit that valence bond theory gives us? What is the point of valence bond theory? Yeah, it does actually kind of say what bonds can't form. If orbitals come at each other perpendicularly, they don't overlap. And valence bond theory says a bond forms when orbitals overlap. So valence bond theory is useful in saying which orbitals can form bonds and what types of bonds they form. Yeah? Valence bond theory also kind of helpful with hybridization. Did we finish hybridization? Did we get to the end of it? Okay. Oh, you know what I want to do? I want to upload these documents so you guys have them on Canvas. I'm sorry I haven't done that yet. Valence bond theory describes that orbitals overlap and give us bonds. Can valence bond theory describe how a bond breaks or why a bond breaks? Certainly not easily, right? I mean, you'd have to say those orbitals no longer overlap. Okay, why? Why did they stop overlapping? Molecular orbital theory does a much better job with this. It explains to us what changes actually occur in those orbitals when they're bonding and why you're able to break a bond. I'm going to upload the last two worksheets that we've done to this Unit 1 on Canvas. Those of you that like to download worksheets will then be able to do this. Download it, annotate, stuff like that. Okay. Valence bond theory also a little bit better at giving us information about structure. Molecular orbital theory, a little less useful for getting information about structure. Okay, I have added those two documents now to the Unit 1, and they're at the top towards the learning objectives. Molecular orbital theory is not something that we'll use to draw a structure and explain things about the structure. Instead, what we typically do is zoom in on specific bonding areas in a molecule. And we use MO theory to describe what's going on with the bonding in that portion of the molecule. We use molecular orbital diagrams, MO diagrams, to help convey this. A diagram is going to have 3 lanes. On the left-hand side, we'll show one of the atoms that's involved in the bonding. On the right-hand lane, one of the atoms involved in the bonding. And then the middle will show the molecule. So let's look at the MO theory for hydrogen, molecular hydrogen. H2, or with its Lewis structure, we'd say H bonded to H. On these outer lanes, we'll show the atomic orbitals. Hydrogen only has one orbital. It's the 1s orbital. What is the shape and nature of the 1s orbital? Perfect sphere, spherical. And there are no nodes. The 2s orbital has a spherical node, so it's like a ball inside of a bigger ball. But the 1s is just a sphere. I'm going to sketch that out for us. Remember that the shading of the sphere tells us something about the mathematical equation. But when it's just a sphere, it could be plus or minus. It could be fully shaded. It could be fully unshaded. It's both at the same time. It doesn't matter which one it is. Is that okay? We said earlier with valence bond theory, when we were getting at hybridized orbitals, we said that these mathematical equations that describe orbitals, their shape, their size, their orientation, can be additively combined and subtractively combined. I don't know if I just made up that word. And that gives us all these new orbitals that come about. Same thing happens with MO theory. We say that if we take both of these while they're in phase, that is, they're both plus, unshaded, or they're both minus, shaded, we get constructive interference. And this actually lowers the energy of the resulting orbital. The new orbital formed is lower in energy than the old orbital. That should feel a bit strange, does it not? How can I add two things together and get something that is more stable? I'm sure there's some analogies out there that we can think about with stabilizing forces by combining things together. But this new orbital is not an atomic orbital, where these atomic orbitals span one atom, but this new orbital is a molecular orbital because it spans two atoms, two nuclei held within that orbital's range. And you'll notice, because these were both in phase, I basically just got a much bigger circle. Or maybe it looks a little bit more like a elliptical shape. What's the 3D ellipse? Elliptical. An elliptical sphere. Oblong sphere. Great. What happens if one of these is in phase while the other, what happens when these are out of phase? What happens when one is positive and one is negative? We get destructive interference, which leads to an orbital of higher energy than the previous orbitals. And again, this would be like taking a shaded sphere and an unshaded sphere and overlapping them. Where those regions overlap, destructively interferes, so they cancel each other out, which means I'm going to end up with this region where I have some positive character and some negative character, but there's a gap in the middle. It should kind of look like a p orbital, does it not? A p orbital, which maybe has a little bit more of a classic clean shape, has one lobe shaded and one lobe unshaded. Okay, these are the new orbitals. And again, the nuclei sit in here. They're still a part of this one molecular orbital. This orbital has a node, an angular node. This orbital has no nodes, but it's still just one orbital in the same way that a p orbital is just one orbital. What are the names that we give to these new molecular orbitals? I think they did a better job naming these than they did naming hybridized orbitals. Again, hybridized names, sp, sp2, sp3, they convey a lot of information. They're just a little wonky for students to learn for the first time. These convey also a good amount of information, but they're also a little wonky. This lower energy orbital is called sigma. That's its name. And the sigma orbital leads to a sigma bond. The high energy subtractive orbital is called sigma star, which is to indicate that it is the anti-bonding version of a sigma orbital. Sigma we call bonding. Electrons that exist in here create a bond. This orbital, when occupied, results in a bond between the atoms. Sigma star is an anti-bonding orbital. Electrons that occupy sigma star do the opposite of form a bond, which is they break a bond. So if you want to form a bond, you need to get electrons from the atomic orbitals into the bonding orbitals. If you want to break a bond, you have two things that you can do. Excite those electrons from bonding to anti-bonding, and the bond no longer exists. Or, with electrons in the bonding orbital, place new electrons in the antibonding orbital, have a species that donates them, and then break the bond. So let's occupy them. Hydrogen, atom, how many electrons will it bring with it? 1. So we'll draw 1 electron on each side. Now for consistency, I'm going to show these electrons as they're going to show up later on. So I'm going to draw 1 up and 1 down. Why is it important that electrons that will pair come 1 up and 1 down? Opposite spin, which means their magnetic fields are opposite, which means these tiny little magnets are going to like each other. Okay, if these hydrogen atoms come close enough for this bonding combination to occur, where will the electrons move to? Will they stay in the atomic orbitals? Will they move to sigma star, or will they move to sigma? Why? Why will they move to sigma? Lower energy. And this is the Aufbau principle that we learn in Gen Chem 1. Aufbau said, fill from lowest energy first, then to higher energy. So these electrons have a new lower energy place that they can go to. There is a calculation that you can do here. You can calculate bonding order. You sum up all of the electrons in bonding orbitals, and you subtract all of the electrons in antibonding orbitals, and it tells you what your bond order is. Oh, you have to divide it by 2. It basically will just say that you've got 2 electrons in bonding minus 0 electrons in antibonding divided by 2. That's 1 bond. And then if you create multiple bonds, you get more complex things in here. You can do all the calculations, and you can learn interesting things that valence bond theory and Lewis structures do not help you predict. There's information that molecular orbital theory gives you that you just can't learn anywhere else. I don't want to get into it, but diatomic oxygen, if you are interested in it, Google it, MO diagram of O2. It actually tells you that there is a bond order of 2 between the oxygens, but that's the result of 2 pi bonds and 1 anti-pi bond. 2 pi bonds minus 1 pi bond gives you just 1 pi bond, but it actually gives a lot more information on how you get to that 1 pi bond. Okay, so if I wanted to break apart H2, I need to find a way to get these electrons into a higher energy state so that the atoms think that they are not bonded to each other, or I need to donate electrons from something else to occupy this orbital up here. This orbital on the bottom is what we call the HOMO. This is the highest occupied molecular orbital. This is considered one of our frontier orbitals. We call it frontier because it's the one that will do the work. It's the one that will do a reaction. These are the highest energy electrons. Okay, in this system, they're the only electrons, but when we get to more complicated systems, we'll look for the highest energy orbital that is occupied with electrons. If any electrons are going to do something, it's the ones with the highest energy. This up here we call the LUMO, which stands for lowest unoccupied. Again, another frontier orbital, because if new electrons will go anywhere, they'll go in by Aufbau principle. New electrons will go to the lowest energy open available spot. Shall we make it more complicated? Yes. Because hydrogen can't do anything else with its bonding. And that's a bit of a lie, because in molecules, the new orbitals that those molecules have allow hydrogen to actually make 2 bonds sometimes. It's called a 3-atom, 2-electron, 3-body bond, 3-centered bond. Anyways, hydrogen, fun stuff. Let's look at an sp2 hybridized carbon bonding with an sp2 hybridized carbon. And in the middle, we'll show the formation of a carbon-carbon double bond. What's the geometry of an sp2 hybridized carbon? Trigonal-planar. It has s, px, and py. Those two axes means that these new orbitals only have access to a plane, the xy plane. And those new three orbitals will try to spread out as far as possible. So a triangular shape on a plane. How many of those sp2 hybridized orbitals does the sp2 carbon have? No, not one. 3. Because it used s, p, and p, and so it needs to get out 3 orbitals. Well, however many orbitals went into hybridizing, it's the number of orbitals that come out. So on each side, I'm going to draw these sp2 orbitals. What other orbitals does the sp2 carbon have? One more time. A p orbital. One unhybridized p orbital. Let me ask you this. Does the p orbital lie higher in energy, equal in energy, or lower in energy than the sp2 hybridized orbitals? Lower? Lily, right?
Yeah. I would say lower.
Lower? Anybody else? Higher? Milena says higher. Unsure?
Can you repeat the question?
Does the unhybridized p orbital, it used 2 of its 3 in this hybridization, but there's 1 p orbital left. Does the unhybridized p orbital lie higher in energy, equal in energy, or lower in energy than the hybridized orbitals? Raise of hands for higher, equal, and lower. We're kind of split. So how would you rationalize it? Anybody that said higher, what would you say? Matthew?
Well, it's not going to hybridize if it's a higher energy.
Not quite, actually, because our p orbitals all started out the same, right?
Yeah.
And s was lower, and then some of the p's did hybridize with the s. So it's not about what energy level it's at, whether it will hybridize or not, but it's more about the necessity. Does it need to become planar? Does it need to become tetrahedral? Does it need to become linear? How many electron regions does it have? But I like your idea. How else can we rationalize whether it's higher or lower? What are you guys thinking? What intuition are you using? Elena?
I'm just thinking that if things combine, then they are going to be reaching a state of lower energy.
Mm. Okay, when things combine, they'll reach a state of lower energy. Not always. Here's what I'm going to argue. The s orbital and the p orbitals combine to find some average of that energy. The s orbital is lower in energy than the p orbitals, but when you hybridize s with p, you should get orbitals that are halfway between s and p. When you hybridize s with 2p, you should get new orbitals that lie a little bit closer to where p was originally, 2/3 of the way towards the p energy, because I have 2/3 p character. So the fact that p's are being hybridized with a lower energy s means that the hybridized orbitals are between s and p. So an unhybridized p orbital will sit higher in energy than the hybridized orbitals. Deal? All right, now if you're drawing this out, I do want to point out, this is qualitative, so ideally these should be the same height. And also we're going to use quite a bit of space up and down, so I try to give a lot of space here so that you have space to draw some lines. All right. Would you guys agree that this bond between C and C, this double bond, consists of 1 sigma and 1 pi according to valence bond theory. 2 sp2 orbitals overlap to give sigma, and 2 p orbitals overlap to give pi, right? So the other sp2 orbitals, those are going to be used to bond to other things. I'm going to pay attention in this diagram to just one of the hybridized orbitals and one, or the only p orbital. You guys okay with that? Seems reasonable, right? I'm only interested in one of the hybridized orbitals from each atom. Okay. I'm going to sketch in what these orbitals look like a little bit. When these hybridized orbitals overlap, they will overlap head-on. That actually gives us a lot of volume that overlaps. The more volume that overlaps, the more dramatic the change in energy. So when an sp2 orbital overlaps constructively, you go down in energy. When it overlaps destructively, we go up in energy. When I take these large unshaded nodes of the hybridized orbitals and I overlap them, I get a large unhybridized node, I get a large node in the middle, and then these little shaded lobes off to the side, those stick around too. So you guys will notice this looks a lot like our sigma orbital from last time, except now it's got these little ears on the side. That's because I'm not just taking S, but I'm taking this sp2 to overlap head-on. When I overlap these destructively, what I get actually looks a bit like 2 sp2 orbitals pointed opposite of each other with opposite shading. Unshaded, shaded, unshaded, shaded. That's because we have put them together out of phase so that in the middle we had a plus and a minus that cancel each other out. What should we call these? Sigma. This is the orbital that creates a sigma bond. It's not 2 orbitals overlapping. It's a new orbital that results from those 2 orbitals overlapping. What should we call this up here? Sigma star. So we're seeing similarities to what we saw with our easier model in hydrogen. Okay, great. I'm going to come back to the P now. I'm going to do P in a different color. Those P orbitals overlap side to side. That side-to-side overlap means less volume actually overlapping, less dramatic changes in energy. So when the p orbitals come together constructively, they decrease. Destructively, they increase. But you'll notice that the new orbitals formed by the p orbitals lay within the range of the sigma and sigma star orbitals. Deal? Now, to be fair, when you squish 2 p orbitals together, you basically just get a fat p orbital, a very wide p orbital. But sometimes this gets tedious to draw, and so you will often see this as just 2 p orbitals drawn next to each other. You could make it a big orbital by just erasing that line where they touch. But for simplicity's sake, we're just going to draw 2 orbitals next to each other. It's one new orbital. The out-of-phase combination, draw them slightly offset from each other and have them be out of phase. Shaded, unshaded, unshaded, shaded. What should we call these orbitals? The orbital that results in a pi bond we call pi. the orbital that breaks a pi bond? Pi star. We haven't talked about non-bonding orbitals. These are bonding, these are anti-bonding. Some atoms have non-bonding orbitals. We won't have to talk about it this semester. It won't be one of our highlights. All right, let's come in and look at where the electrons are going to fall again. On one carbon, I'm going to show the 4 valence electrons that it brings. All of them spin up. And on the other carbon, I'm going to show the 4 valence electrons that it brings. All of them spin down. Why? Just for consistency, when they come in, they make a pair. Remember, there's 2 orbitals on each atom that we're ignoring. I'm looking at a carbon-carbon double bond. So how many total electrons am I considering? 4. 2 and 2. When I take what's left over, 2 and 2, I'll get 4 electrons in my new MO diagram. Okay. I've got 4 total electrons that I'm going to use. I'm going to start with the off-ball principle. I fill lowest energy first. That's sigma. I'm going to follow Hund's rule and the Pauli exclusion principle. So I do 1 spin up and then 1 spin down. That orbital is now filled. I still have 2 electrons left to go. I move to the next lowest energy. That's my pi orbital. 1 spin up, 1 spin down. That's all of my 4 electrons. I'm done. We could do that bond order calculation that says 2 plus 2 minus 0. There are no electrons occupying antibonding orbitals. Divided by 2 says a bond order of 2. Great. That's what valence bond theory said too, bond order of 2. Now using these names, sigma, pi, pi star, sigma star, by a raise of hands, who can tell me which of these orbitals is the HOMO? Use the name. Sigma is the HOMO. Sigma is the highest occupied molecular orbital. Yes, highest energy occupied orbital. Good. Sigma would actually be considered the LOMO, the lowest occupied molecular orbital. We don't usually talk about the LOMO because it's not a frontier orbital. To get the lowest energy electrons to do something, I'm first going to have to get rid of those higher energy ones. Those are the ones that are more reactive. So in this case, pi gives me my HOMO electrons. Where is my LUMO? Pi star. So in OCHEM 1, you learned a lot about alkene addition reactions, correct? And we talked about how the, yes, I was there, you did. We talked about how the pi bond is involved in that addition step. The pi bond always breaks. Why? Valence bond theory cannot tell you why the pi bond breaks and why the sigma bond does not. Valence bond theory gives you the shape, the overlap, the character, and valence bond theory might be able to say, oh, well, the p orbitals don't overlap as much, so it must be easier to break. But that's just vibes. This is math. This tells us, because of that orbital overlap and the actual equations that are produced, the pi orbital is the highest occupied. So if any electrons are going to leave from the alkene, it's the pi electrons, not the sigma. And the pi star is the lowest unoccupied orbital. So if any electrons are going to come in, it's going to break the pi bond before it breaks the sigma bond. Frontier orbitals. They tell us what is going to happen in a step. And when it comes to pi bonds, double bonded systems, it's always the pi bond that breaks before the sigma bond. That's why I love MO. And I have had students tell me time and time again that my exams focus and hit on a lot of understanding and conceptualizing what's happening, and this is part of it. So while I'm not going to have you guys draw molecular orbital diagrams this semester, I'm rarely even going to have you draw orbitals at all. This is the foundation for explaining all of the reactions that we're going to explore. Why does it happen? MO theory tells why it happens. Not a very useful way to communicate about structure, though. Here's another question that I had when I was first learning about molecular orbital theory. If the electrons only occupy sigma orbital and pi orbital, why do we even care about sigma star and pi star? Why would they even exist? You guys might understand that these orbitals all overlap in space, correct? Because the nuclei are centered here, here, here. The nuclei are in the same place. These are just different shapes, sizes, and orientations, all overlapping in the same physical space. So why would we even care about these orbitals if they don't have electrons in them? It's not about whether electrons are there or not. It's about what those orbitals tell us about the electrons when they get there. If I can get electrons to make this shape, I have a sigma bond between my atoms. If I can get electrons to make this shape, I can break a pi bond between my atoms. All I need to do is get electrons to have an equation that is this shape, and now I have a lot of information about it. And maybe that gave you more questions than answers, but that's what I like to think about. Okay, questions on molecular orbital theory? Great. I will occasionally come back to this as a reminder about why reactions are happening the way they do. But maybe less than a handful of questions will ever really touch on the challenging nature of MO theory. Okay? All right. Let's talk about bond line structure. There's an age-old saying, when you assume, you make an ass out of you and me. Right? Because that's how you spell assume. What is that really trying to say? It says if you ever assume something without explicitly saying it, then I might not assume the same thing. We'll be on different pages because we're assuming different things, and we're going to run into issues. There's a famous example of this where a NASA project was coordinating with the European Space Agency on a NASA and European Space Agency project was collaborative, and people were assuming that all of the measurements being made were in metric measurements, like grams and centimeters and all that kind of stuff. But not everyone at NASA was, and they weren't writing out their units, and so people were assuming what units were being communicated. And because of that, the project ended up having catastrophic failures because the components that needed to work together didn't work together. They didn't fit because people had made assumptions. Okay, we are going to make assumptions in bond line theory, or bond line structures. So we need to be on the same page about the assumptions. We have to agree on the assumptions. And the hard part is that you don't get to negotiate the terms of the agreement. You just have to agree to the assumptions that have been established. All right, here's how I like to go through it. Number 1, assume carbon at every end and bend with enough hydrogens to satisfy octet or charge. And here's the deal, you don't have to make that assumption. You can sometimes explicitly show those carbons. This happens a lot with methyl groups at the end of a chain. You'll see a chain and then it ends with a line pointed at CH3. The deal is, if you're not going to assume the carbon, you can't assume the hydrogens either. If you're going to explicitly show the carbon, you should explicitly show the hydrogen. Butane. Also butane, but two of the carbons have not been explicitly assumed. I don't know. I don't know what you're trying to get at. What are there hydrogens there, or is it just a carbon? Right? This is kind of that middle ground where you have assumed the hydrogens but have not assumed the carbon, and it's the hardest one for me to interpret. So for this reason, avoid this. This idea of every end and every bend, I stole that from a student who gave me that wording. Here's an end on the left-hand side, and here's an end on the right-hand side. The line just ends at nothing. If it ends at another atom, well, it's not really an end. You shouldn't assume a carbon there. It's telling you what atom it's pointing at. And then these are the bends. I think the hardest functional group for students to sometimes assume the carbons at is in the alkyne. Because there's no bend in the middle of that carbon chain, but there is an end to a bond. Here is a sigma bond, a single bond, and it ends right here, which means there's a carbon at the end of that bond. Coming from the other way, that's the end of a triple bond, so every end and every bend. Okay. Assumption number 2. And this is, I think, maybe the assumption that most OCHEM students should actually avoid doing. I get feedback from students a lot that say, if I hadn't made that assumption so often, I probably would have understood my structures better. And that is that you can assume lone pairs. We will draw a lot of lone pairs if we're not assuming them. But assuming the lone pairs often means you forget how many lone pairs there are. And so you remember that activity we did last week? I had you fill in that diagram, and we drew in lone pairs when we were looking at bonding patterns and charges. You don't have to draw those in, but the more you draw them in, the more familiar you'll be with the bonding patterns. I think that's it for the things that we assume. And now I want to clarify the things that we will never assume. The only time a structure should not have a charge is if it's neutral. Like every atom has a formal charge of neutral. Or unless I'm assessing you on your ability to determine the charge, right? In which case, I have to show you all of the lone pairs, because you can't assume both charges and lone pairs. You really can only assume one or the other. Without at least one of them, you don't have enough information to understand the other. Never assume radicals. We can assume lone pairs, but we should not assume radicals. Any idea why?
Changes the characteristic.
Yeah. Well, first of all, radicals aren't pairs, right? So they're definitely not included in that statement about assuming lone pairs. Radicals are highly reactive, so if there is a radical, it's probably playing a role and you should show it. And it can impact your formal charge calculation. So it's useful to show those radicals. I don't ever assume radicals when I'm drawing them, and I don't want you guys to either. Never assume heteroatoms. I'm going to add to that, but first, who can name off a heteroatom? Oxygen. Nitrogen. Hydrogen is not a heteroatom in organic chemistry because organic chemistry is the study of hydrocarbons and their derivatives. Good try. Halogens, fluorine, chlorine, bromine. However, I told you guys about how iodine is pronounced differently than all of the other halogens, despite being spelled the same. Fluorine, chlorine, bromine, iodine, iodine, bromine, chlorine, fluorine. Why don't we pronounce it the same? I think iodine got into the American vernacular during the Cold War, and then because of that, it changed its pronunciation based on like how most people wanted to say it. I don't know. What else? Sulfur, boron, phosphorus, sodium, all of the metals. So heteroatom is everything other than carbon or hydrogen. All right. Never assume heteroatoms, comma, or the hydrogens they're bonded to. We can assume hydrogens on the carbon chains, and we assume enough to satisfy the octet or the formal charge. But we should never assume hydrogens on heteroatoms. This is actually a common mistake I see in OChem 1. Early on in the semester, they'll be told to transcribe a structure from bond line or from Lewis structure into bond line, and they'll assume hydrogens connected to oxygens, assume hydrogens connected to nitrogens. We can't do it. We've got to show them. That's just the rules. All right, I want to do a couple of exercises with them then, shall we? How many hydrogens in the structure on the left and the structure on the right? Take a minute. Convince yourself. Look back at that table we made last week. How many hydrogens on the left? Tert, butyl, cation. How many hydrogens on the right? The N-butyl anion. Now convince your neighbor. How many hydrogens? I'll be your neighbor, Lamb. Good work. What'd you find, Max? Good work.
This should have 3 on the end and it's negative, so.
Okay, I know that this one will take a while to copy down, so I want to give you a chance to go over it over break, but I want you guys to work on this and determine what charges are missing. All hydrogens and all lone pairs are shown. This top one, how many on the left?
9.
On the right? 9. Did this group say 10? So let's proof it, right? On the left, here's an end. So there's a carbon. That's going to be a methyl group, CH3. Because I see one bond explicitly shown to that carbon, and I know it must have an octet because it's neutral, which means it needs to have 4 bonds. Neutral carbon has 4 bonds. Or a radical, and the radicals are not shown because we can't assume them. So if I see one bond explicitly and I need to have 4, that means there must be 3 missing bonds to hydrogen. That's enough hydrogens to satisfy its octet. The carbon in the middle has 3 bonds shown explicitly, but it does not have an octet. That's what the formal charge indicates. It's short on a bond. So instead of having 4, it should have 3. That's what it has. So that carbon in the middle has no hydrogens. On the right, we have the same thing, a CH3 at the end, a CH2 in the middle, 2 bonds explicitly shown, no charge, so it must have an octet, 2 bonds missing. The same thing here, CH2. Now on the end, I've got a carbon with 1 bond explicitly shown in the backbone and a -1 formal charge. What does that indicate to us about the carbon? It indicates a lone pair. Every time carbon has a negative charge, it has a lone pair. Now that lone pair was assumed. Because the formal charge was not, you were able to deduce that it has a lone pair. Okay, 1 bond explicitly shown, negative charge implied. A lone pair implied by the explicit negative charge. So that actually means that I've got essentially 2 bonds. So to get to my octet, I only need 2 more, which means this is a CH2 group. Interesting example, right? These are not structural isomers. Despite having similar chemical formulas, this is C4H9+, and this is C4H9-. So they're not isoelectronic with each other, which means they can't be chemical structural isomers. But an interesting analogy, right? All right, feel free to copy this down. Let's take a 5-minute break and come in just before the 3. Try to figure out what charges are missing in this structure based on all bonds shown, all lone pairs shown. But otherwise, take this chance to get up, move around, stretch your legs, get your blood flowing, get more water.
from those two molecules, is any of them, are any of them like more stable in nature?
Oh, I mean, they're definitely reactive in different ways.
Okay.
I think it's easy to argue that the structure on the left is more stable than the structure on the right.
Okay.
But in terms of swapping the charges, for instance, putting a positive charge where the negative is and putting a negative where the positive is, would make each structure respectively much, much less stable. So the positive charge being on the most substituted carbon makes it more stable.
Right.
The negative charge being on the less substituted carbon makes it more stable. Putting the negative more substituted and the positive less substituted destabilizes them both. Carbons in general are not good at holding lone pairs. They're not electronegative, which means they share electrons well. Carbons are better at holding positive charges, but they're happy to take electrons because again, they're not electronegative. They're happy to take electrons from another species. So they're definitely both reactive. But I think that you can actually get salts of both of them.
Salt?
Yeah. Well, you know what a salt is.
Yeah, like
Cation, anion pair. I mean, you couldn't get a salt of that combination.
oh, okay, that's what I was
No,
thinking.
sorry. They would violently react.
Yeah,
They'd form a carbon-carbon bond.
okay.
But I think that, so we'll talk about the structure on the right. It forms a salt with lithium,
Okay.
but the nature of the salt is actually much more covalent than ionic. And then the structure on the left, I guess I don't know if I've heard of a salt with it, but I feel like you could, given the right anion, I feel like you could make it happen.
Yeah, but it seems like the charge is like balanced for like the substituted carbons. So would it be like less reactive to it?
No, I think, so the structure on the left
Yeah.
is able to kind of shield that positive charge because of the carbons surrounding it,
Right.
which means that it actually would prefer an ionic pair better because those ionic pairs are separate from each other. Covalent bonds are usually shorter, and ionic bonds are longer.
I see.
So that shielding would make it easier for it to not form a covalent and for it to maintain ionic, compared to if the positive was on a less substituted carbon.
Okay.
Yeah.
That makes sense.
Good.
Thank you.
Mm-hmm.
Yeah. I was reviewing the video from last year and like
Yeah.
it's coming back to me.
Good. I'll love to hear it. You can see Ryan used this board too. You know what those are?
Who was doing resonance on that board?
Totally. Resonance with an aromatic ring. Here's the hexagon. And then a group coming off of it, probably a CH2 plus because it's got a plus sign. But he doesn't shade his p orbitals.
No, he does not.
Ever?
Not really.
Oh, interesting. I thought it was so funny when I learned that the other two full-time faculty that teach OChem never touch on MO. Is that true? You guys that took Ron and Ryan, never touch on MO?
With the Ron done.
I think you learn it in Gen Chem.
Yeah.
In Gen Chem, like, because I took Gen Chem with Ryan and he went over it like so much that like anybody that,
MO.
yeah, like orbitals.
When? No, orbitals or MO theory?
At the U, they go over. They do MO.
Because we do
You do the math with the equations to like do the.
bond order. It's a nice equation. I think it is better suited for Gen Chem than OChem. Like it just doesn't matter in OChem. We do spend a lot of time on orbitals,
Yeah.
defining orbitals and hybridizing orbitals. But actually at SLIC, we don't teach MO in Gen Chem. It's something that Ryan makes optional. He's the course lead for Gen Chem 1. He makes it optional for instructors to include, but generally, like, he encourages people to not do it. Really? Did you learn other orbitals in Gen Chem 2? Or just MO theory?
Well, we learned like general orbital theories in Gen Chem 1. but
Sure.
then went more
Hybridization.
went more into MO in Gen Chem 2.
Oh, interesting.
Yeah.
I wouldn't have thought Gen Chem 2 was the place for it.
They also do like a lot more NMR at the U and like OChem 1 than they do here, I feel like.
I guess it depends. You know, Ryan sometimes runs out of time to do NMR
I have Ryan, so maybe
because it was at the end of the semester. And he actually changed the way that he changed his sequence based on listening to me talk about my class. I teach all of spectroscopy right before the midterm. We learn it before we go into the reactions, because how else can I tell you that a reaction really happened unless I can show you data from the reaction showing you how the structure changed. And you don't learn that spectral interpretation until the end of the semester. It just doesn't work for me. And Ryan was like, I agree, and so I'm gonna bump it forward.
That actually is so helpful because I was so confused why we did it in lab.
Yeah,
I was like, this
that's why it
makes
showed up so
zero
early.
sense. Yeah.
I loved the way you taught it.
Yeah, thank you. I didn't used to. Early on, I used to teach functional group by functional group. And the first functional group our textbook goes through is alkane, which is such a boring functional group to go over. And so I would actually teach NMR, IR, and mass spec of each functional group as we got to it. So I'd start a new functional group here. We're going to talk about alcohols and alkyl halides. Here's the IR and the NMR and the mass spec of it. We're going to talk about ketones. Here's the IR, the NMR, and the mass spec of it. And then I realized it just wasn't super effective because we don't cover all of the functional groups in OChem 1. So then I'm like sending you out on your way with partial information about IR and NMR. Doesn't make sense. But it needed to be earlier. It needs to be much earlier. Yeah, so MO theory in Gen Chem 2 seems wild. I never learned MO theory in Gen Chem when I was in college. I learned it in inorganic chemistry. I never heard about it in OChem either. And then I went to TA at CU Boulder, and they taught MO heavily in OChem 1. And I have found the middle ground. I try to find the middle ground on MO theory because it is the best explanation for bond making and bond breaking. Why things are allowed to happen and why things aren't allowed to happen. But it's heavy. It's like weird stuff. And it's messy. It's so cluttered. I used to do this all in one color. You couldn't see anything. Okay, what charges did you guys find on that structure? Raise of hands. Katie?
The oxygen on the very bottom has a negative charge.
Great. All right, who's got another one? Ella?
Nitrogen is a positive charge.
Nitrogen's got a positive. And let's do Max.
Bromine has a positive on the top.
Nice. How hard was that? What did you need to lean into to do it? Looked at that chart? Did you feel familiar with some of those bonding patterns? Like, oh, an oxygen with one bond, negative charge. Oxygen with two bonds, neutral. Nitrogen with four bonds, no lone pair, positive. A halogen, who was it last week that said this was cursed? Yeah. That halogen with a double bond, cursed, positive charge. You get familiar with those bonding patterns, and technically you wouldn't need the lone pairs, right? But you can't figure out the formal charges unless the lone pairs are shown. And working backwards, if you don't show those charges, you'd never be able to figure out what lone pairs are needed there either. Okay, good work, guys. We're going to move on to that second sheet, the one that I just handed out. All of your favorite things. CARIO, equilibrium, resonance. If you guys watch my fall OCHM 2 recordings, I fell really far behind. And I think it's in part because I was writing these learning objectives documents. Did I show you guys those? I kind of want to show you them, but this screen is such an annoyance. In the fall, I put together learning objectives for all of my classes. And what I've come to realize about the learning objectives for this class, they're all very similar as we get later in the semester. And they're basically just a list of all of the reactions that I want you guys to be able to show me. So I think the longest learning objectives for one of the units is 5 pages. And it's thorough and it's repetitive. There are some reactions that are listed more than once because they kind of show up in different ways, in different perspectives. So I know that can come across a little overwhelming, but I think it's better than not having it at all. So here's your Unit 1 learning objectives. I'm starting to use this document as a guide for building my worksheets. You'll notice that learning objective number 1, interpret bond line structures for formal charge and hybridization states. We've done it, right? We have looked at our structures for hybridization, for their bonding patterns, for their formal charges. Describe bonds through valence bond theory and MO theory. Check. Use CARIO to compare acids and bases. This is where we're headed. Resonance, contribution, nomenclature. And then this is what I'm talking about when I say all semester is going to feel very long, these learning objectives. I will list out all of the different reactions, and if there are unique conditions within those, I'll list those out as well. And we'll learn a lot of reactions. This is one reason that I will give you a cheat sheet on the exam. It's because there's a lot to cover, and I don't want you to think that this class is about memorization. It's really not about memorization. It's about comprehension. It's about using your tools. So as we go through these learning objectives, I would encourage you to be building cheat sheets as you go and highlighting which reactions you've got down that you don't need on the cheat sheet and which reactions you need to put on there. Yeah? So I want you guys to use this as to your advantage this semester. Okay. So some of you may have had me, before I started calling it CARIO, I used to call it ARIO without the C. And I actually used to, I used to try and spell it with an E in there because the A is not descriptive enough. So let's go through it. Let's start with the C in CARIO. C stands for charge. This is not an all-encompassing rule, but as a general guideline, more positive means more acidic, more negative, more basic. Are you okay with that shorthand? It's a good way to remember it if you're going to incorporate it onto your cheat sheet, right? So you've got an example. Unfortunately, it wasn't my first row. Whoops, I went out of order. So if you look at that second column, these are all versions of acetic acid. The top form is protonated acetic acid, then neutral acetic acid, then deprotonated acetate. Which of those structures is the most acidic? Why? It has the most positive charge. If any of those structures is going to give away a hydrogen, it is the structure that has a positive charge. If any of them is going to take a hydrogen, it's the one with the more negative charge, the one that's more willing to accept H+. Now, here's an exception. If we look at HSO4 minus and H3O plus, which of these is more acidic? HSO4 minus is more acidic than H3O plus. Why? Because of compounding factors. Different things incorporated inside of CARIO can kind of affect each other, right? So the fact that sulfate has 4 oxygens and a sulfur, it's got inductive effects, resonance effects, atom effects, and so you can't always rely on that. So this is an exception. Well, an example of an exception. Deal? Okay, A stands for atom, but we're going to look at this in 2 different ways. First, we're going to look at in a row, comparing atoms that are in the same row as each other. Increasing electronegativity is increasing acidity. More electronegative is more acidic. Why? To give away H+, to be an acid, that species has to keep the electrons. What species are good at keeping electrons? Electronegative species. So the more electronegative, the more willing it is to give away the H+ and keep the hydrogen. And then we can flip this and say less electronegative, or actually if you like to keep things equally correlated, you can actually say more electropositive. It's not a term we use a lot, but it's the opposite of being electronegative. It's something that prefers to be more positive. More electropositive is more basic, more willing to use any electrons that it has to donate to a hydrogen ion. The other comparison that we make between atoms is when atoms are in the same family. Here, we don't consider electronegativity, we consider size. Increasing size equals increasing acidity. Larger atom, more acidic. So if we consider a family like the halogens, HF, HCl, HBr, HI. First of all, which of these contains the most electronegative atom? Hydrofluoric acid, and like literally the most electronegative atom. Which of these is the least acidic? Hydrofluoric acid. Hydrofluoric acid is super interesting. You guys watch Breaking Bad? The guy grabs hydrofluoric acid out of his high school stockroom. No way. We don't even have hydrofluoric acid here. Labs that use hydrofluoric acid have big labels on the outside that say, "Caution, you may die if you come in here." Super scary. Not because of its acidity, but because of how it reacts with minerals. It's really good at eating through minerals better than most acids are. It actually doesn't interact much with your flesh at all. So not very acidic, dangerous for much stranger reasons. Most electronegative, but least acidic. Least electronegative, most acidic. So why? If fluorine is so good at pulling on electrons, how come it's not better at taking electrons away from H plus than iodine is? That's a part of it. Fluorine is small. So actually the orbital overlap that fluorine has with hydrogen is pretty good. So its bond is arguably stronger. It also comes down to the size, contributing to polarizability. If you can get H plus to be this little dot and F minus to be this little dot, how well can those atoms polarize themselves? Or in other words, delocalize the charge to one part of the atom? Not very well, because they're very small. But H plus compared to I minus is very polarizable, meaning it can take that negative charge and it can push it to one side of its atom, essentially creating a much more negative area and a more positive area. If it places that more positive area next to where the hydrogen is, positive and positive repel. So rather than based on electronegativity, this is based on acidity. Polarizability. We're talking about acidity. How well can it polarize a charge? Now, I think you guys can imagine that these two components, going across the row and going across the column, they can be compounded, right? What if you wanted to consider how oxygen compares to a halogen? Well, you need to go across the row and also down a column. And so when you have that compounding orientation, move to the bottom right. Whatever is further to the right and lower is going to win. But if you compare it opposite, it gets a little more confusing because you get less electronegative and larger, and it's just kind of weird. So a lot of times you'll see that this stays simple. Keep it in a row, keep it in a family, or have them compound together and move to the bottom right. All right, you've got another set. This is the middle column. At the top, we have an SH group and an OH group. Which is more acidic, the SH group or the OH group? SH is more acidic than the OH. Why? Sulfur is a larger atom in the same family as oxygen. So even though oxygen is more electronegative, sulfur is more polarizable. Rather than it wants a proton, it gives away a proton more easily. All right, the second family, or the second molecule, swaps that SH for a CH3. What's more acidic? A hydrogen from the carbon or a hydrogen from the oxygen? Why? Oxygen is more electronegative. Carbon and oxygen are in the same family. All right. Collaborate with your partners next to you. What's more acidic, the NH2 on the left or the OH on the right? Drive safe. Oh, yeah, sorry. I knew I was forgetting somebody. Mm-hmm.
I sure don't.
Because N So then it's more electronegative, so it's more acidic as well.
Are nitrogen and oxygen in the same family, in the same row, or neither? They're in the same row. So we're basing this on the first component of ARIO, which is, by the way, this is why I used to spell the A with A and E. I'd go by atomic size and electronegativity. So if you wanted to, you could in theory spell CARIO like this, and it would maybe help you distinguish the two components of comparing atoms to each other. So nitrogen and oxygen are in the same row, meaning we identify the more acidic atom as the more electronegative, which is oxygen. Great. Now, I could have made this a little bit more challenging, and maybe I should have, but I apologize. I put this together right before class after my lab. What if we had done this? Compared NH2 and SH. Are they in the same family? No. Are they in the same row? No. And so actually I was going back to what I was saying about compounding effects. This is where it gets challenging, right? Which one's more electronegative? Nitrogen is more electronegative than sulfur. Which is more polarizable? Sulfur. So if sulfur is more acidic than oxygen and oxygen is more acidic than nitrogen, therefore sulfur must be more electronegative than nitrogen. Yeah? You can't easily make a direct comparison between nitrogen and sulfur, but since you already made a comparison between sulfur and oxygen and nitrogen, we now have a comparison between sulfur and nitrogen.
The nitrogen that we've been seeing here is kind of like a bit of an amide group or something.
It is an amide, yes.
I usually think of those as being basic, but how do you make the distinction between them being like acidic?
Well, that's a great question. How do you distinguish between an amide acting as a base or acting as a acid? Generally, it's the pH of the conditions that you're in. Is there a surplus of hydrogen ions floating around? The amide is not likely to donate hydrogen ions if that's the case. And it very well may accept hydrogen ions. Or is the pH more negative? More positive? Is it a more basic environment? Are there species that are willing to accept hydrogen ions because in that case, the nitrogen may donate the hydrogen ion as an acid? Did I say that? I think yeah. So in acidic conditions, the nitrogen is likely to accept a proton. In basic conditions, it's likely to donate a proton. Depends on what conditions it's in. At neutral conditions, it really varies. It may not do anything at all, right? It just may be better stable as neutral. Sarah?
If the nitrogen was a carbon, would it still be SH being more acidic?
Yes.
Since it's more like right on the periodic table?
For the same reasons, actually. We know that carbon is less acidic than oxygen, and we know that oxygen is less acidic than sulfur. Therefore, sulfur must be more acidic than carbon. Yeah? Good question. But it's kind of that same orientation that we saw for nitrogen and sulfur. They're not in the same family, they're not in the same row, but they kind of slant down to the right, and so you can kind of gauge that whatever is further down to the right is going to be more acidic. Okay. The R in CARIO, what does it stand for? Resonance. You know what explains resonance really well? MO theory does a great job explaining resonance. In fact, it depicts resonance closer to what the molecule actually experiences than valence bond theory and Lewis structures. Here's what we say. Increasing resonance in the conjugate leads to increasing acidity or basicity. Stronger acid, stronger base. More acidic, more basic. If you want to consider how good of an acid it is, look at its conjugate base and look for resonance. If you want to know how good of a base it is, look at its conjugate acid and look for resonance. So a quick reminder on resonance, we can use the 3-atom rule. That is, have a pi bond plus a lone pair and or a charge. And make sure that those exist across 3 atoms. 2 of those atoms will need to have the pi bond. The other atom will have the lone pair or the charge. So if you want to, you can say atoms 1, 2, 3. They don't need to be numbered that way, but it's a good way to get familiar with recognizing resonance patterns. Here's a resonance idea that I came up with for a bonus question once. Let's say that acetic acid gets protonated. There are 2 possibilities of what could form. Take a minute to copy them down. Work with your groups to decide which of those forms is more likely to exist. In other words, which of these oxygens is more basic? Which of these oxygens is more likely to accept the proton? And look for the possibility for resonance. Man, the time flies when you're talking about acids and bases. All right, chat. What did you decide? Talk with each other. Which oxygen is more basic? You know what, I think my hint is actually probably more detrimental than helpful. That little thing I put in red, actually, I'm not going to encourage you to think about how, it's not always going to be like that. This is a challenging one, so I'm curious to hear back. Sorry, keep going. What did you say?
We were saying this one maybe just because this participates 1, 2, 3.
And the other one doesn't?
It just combines these two together instead of separating.
Yeah, but do you have a 3-atom system that has a pi bond, a lone pair, and a charge? So you're saying you've got a pi bond and a charge. What would be your third atom if you were going to consider? Obviously, these two have to be part of the three because they're part of the pi bond. What would be the third? What? The hydrogen? No, let's not assume the hydrogen. Hydrogen can't do resonance because resonance is the delocalization of pi electrons. Hydrogen can't have pi bonds. Yeah. All right. Any ideas? Which of these is a more stable conjugate base?
The bottom.
More conjugate acid? Bottom is more stable, meaning that this is more acidic. Anybody else? Anybody agree? Raise of hands. Okay, I know you guys agreed, but I might have changed your mind. Okay, does that mean that everybody else agrees that the top oxygen is more basic? Or raise your hand if you would leave this blank on an exam. All right. I think that my hint actually really didn't pan out well in this case, but a lot of times it does.
Yeah, no, I was thinking the top one could potentially have resonance by leaving a carbocation, but.
So actually, yeah, anytime you have a pi bond, you have the capacity for resonance by just putting those pi electrons on either carbon. But what we want to imagine here is having resonance through the three-atom system. So this top structure, it does have a pi bond, a charge, and a lone pair across the three-atom system, but actually the lone pair and the charge are on different atoms. So it's this lone pair that I would want you to identify as being able to be shared with that central carbon, while the pi bond is taken by the oxygen on the top. This is only the movement of pi electrons, so this counts as a resonance form. And you'll notice that across that three-body system, three-atom system, we've moved the pi bond and we've moved the charge. The one on the bottom doesn't work for resonance. If I try to take the lone pair from the same oxygen and move it in the same way, I'm going to create a +2 charge on this oxygen, not great, and a negative charge on the other oxygen. So I'm not stabilizing charge by any means. And if I try to move it backwards, if I take the pi bond away from the oxygen on top towards the oxygen on bottom, I break the octet of the oxygen on the bottom. I start giving it more than 10 electrons. So there is no resonance for the form on the bottom. The way that we could redraw the structure on top we could show it as its resonance hybrid, which is that there's a double bond in both directions and the positive charge is delocalized. Okay, so what we found out is that the oxygen on top is more basic because it has a more stable conjugate. Meaning that conjugate is less likely to give away the proton it just received. The conjugate on the bottom, if formed, is likely to give back the proton and reverse the equilibrium. All right, we're running out of time. The structures on the far right were meant to help you talk about resonance while also looking at other compounding effects. So the very top structure, if one of those hydrogens gets removed, there is the capacity for resonance in the conjugate base. This is an example looking at the conjugate acid. But when we look at the conjugate base that forms, here's that CH3. It becomes a CH2 minus with a lone pair. And that CH3 minus is in resonance with an O minus. And based on atoms, we know that the oxygen, more electronegative, holds on to that negative charge better. The other structure was an aromatic ring with a CH3. And the conjugate base of that CH3, again, is a CH2 minus. And there are 3 other resonance forms where that negative charge is shared by atoms inside of the ring. And then lastly, a shorter chain, again with a CH3 and less resonance. So we start looking at this only has 1 other resonance form, less resonance than 3 other resonance forms, less stable, less acidic. But a resonance form where oxygen takes the negative charge, despite having less resonance forms, is more acidic. So, most acidic on top, least acidic on bottom for that series. Interesting? It's not always the most resonance. It starts to compound with other things, like what atom is holding on to the negative charge. Okay, we're going to look at induction and orbitals next week. And not next week, next class, Thursday. And we're going to talk a little bit more about equilibrium and a little bit more about resonance before we start looking at reviewing all of our reactions from OCHEM 1. Okay, see you guys Thursday.